to the 바탕화면. Oh. I think there are some lecture notes that are not ours, so probably we have to better make a new directory. Info 2022, and can put this one right there. That one, this one. I think that's ours. Okay. All right. And I believe we were doing this one. Okay, last time we were doing this, and now we need to do the rest. Okay. All right, that's good. So today is Monday. How many students? 1, 2, 3, 4, 5, 9, 10, 16? Excluding 이스티악. So 이성규 학생이 학회에 참석한다 그랬으니까 다 온 거네. 그죠? 오케이. 그러면 다 체크를 하면 되지. All right, I think we are ready now. Okay, so last time we talked about horse race problem, this one, and then we have a coding table. Basically, this is a coding table, right, for each corresponding to the name of a horse. Horse 0, assigned code word 0 with the length 1. Horse 1, assigned code word 10, which is length of 2, and so on down the line, right? So, and then we have shown that in this particular example, this code, which basically the assignment to the name of the horse, achieves the lower bound, right? Maximum lower bound, right? Which is the entropy. Okay, and then let's suppose that there is a genius who claimed that, you know, I have designed the assignment which is better than this. Then what can you say about him? Let's say there is a person which is known to be genius, right, in GIST ECS department, and then he claimed that he came up with a coding assignment which is doing better than this, right? And then what can you say to him after you have taken this course? Someone is claiming that he has a description system which is doing better than this largest lower bound, right? Then what can you say? Impossible. Okay. Yeah. So okay. So any practical coding system should be lower bounded by this maximum one, right? So if someone claims that I have a better system, then nonsense, right? You must have made a mistake somewhere, right? That's what you can say, because it is not possible to design such. Okay, so that's the powerfulness of a fundamental bound like entropy and the mutual information and the capacity. Like when we talked about on the board the other day, we were trying to design a repetition code, right? And that's kind of doing an assignment, right? And then what was the question that we said we have to remember, right? You have to compare this with the probability of error for a single channel use, right? Can we do better than this, right? And then make the probability of error goes down to 0, right? That's the question we should remember, right? Rather than solving the problem right at that spot, that is not important because we can do that, right? But remembering that we had that question is very important, okay? Because we will talk about that in chapter 7, okay? All right, so that's that. And I guess this one is pretty clear, right? So we talked about information. Basically, we define the entropy as the average information, right? And then information was defined as 1 over p, the probability of occurrence of that outcome or event, right? And this one has the highest probability, right? And then if you take log 2, this is 1, right? And then it was assigned to be the length 1 code word, right? It was assigned to the length 1 code word. How about in this case? If I invert this and take log 2 bit, right? So it was assigned to length 2 code word, and so on, right? So with this example, it makes sense that Shannon has designed, coding system that is making sense, right? In this particular, I mean, if you were the one, if you were designing this coding system, you would do the same, right? Because you have agreed with me when I asked that question, right? This one has the probability of half. One would you like to ask first to be the winner? And then you said, the first one makes obvious, right? So Shannon's design is not a surprising one; it's an obvious one, and then that design makes sense, right? Okay. All right. So that's about it for this motivational example. Okay. So in this particular case, one more thing I would like to say is that this is the part of source coding problem. Okay, source coding try to remove the redundancy and make the smallest description system as possible. Right? That's this example. Okay, when we go to the coding theory example, channel coding theory example. Then we are going to increase the redundancy in order to make the probability of going over the channel. So in order to make the probability of error goes down to 0, right? As the shortest amount of redundancy added to it as possible. Okay, so the objective is a little bit different, and not a little bit different, completely different, right? All right, so that was the motivational example. Now we want to move on with the other part of the definitions. Okay, so that motivational example gave us the reason for studying these fundamental bounds, fundamental numbers. Okay, and joint entropy in this page I would like to define. And the conditional entropy. Okay, joint entropy is defined this way, where it is written this way: h x comma y. So that's just a notation of this textbook. If you write your paper, you can define different notation as well. If the joint entropy of a pair of a discrete random variable x and y with a joint distribution p x and y, this way, is defined as, if you write a paper, probably what would you do? P x and y, and then you need to define x belong to a certain set, y belong to a certain set. But I am for the sake of convenience, removing those, right? If I add all of them, it becomes a textbook, right? We don't want that, right? Okay, so but if you write a paper, then you can make it precise by defining the range of this random variable. Okay, so x belongs to a certain set, y belongs to a certain set, and so on. And then obviously also when you do the summation, x belongs to that set that we have defined, y belongs to that set that we have defined, and that's the obvious thing. And then this joint distribution and log of joint distribution. I didn't do the inverse. Why? Because I have taken minus sign outside. Okay? And then I can talk about this one in terms of expectation. Okay? Expectation of a random variable. Okay? So in this particular case, right, I can treat the probability assignment as a random variable. Okay? Probability assignment as a random variable. Okay? So I have taken first map. Okay? From xy tuples to probability of x and y. Right? So this is an assignment. Okay? Random variable is an assignment plus distribution, right? So I'm talking about the assignment part, okay, of a random variable. So x and y tuple map it to p x and y. I have done that, okay. And then after that, I am doing one more mapping from that pxy to log of pxy, right? So I have taken function 2 times, right? And this one is can be done, right? 1-to-1 correspondingly, right? Then I can treat this as a random variable or not. It's a random variable, right? I have taken the function twice, right? Mapping from input to output, from this output to another output. If I concatenate the two mapping, that's the log p of x and y, right? So I have came from the sample space to this random variable's range space, right? And then I can treat this as a random variables assignment, right? So I can just treat this as a, let's say I call it random variable. Let's say whatever the name that you would like. Let's say y. I can do that, right? So I can call this shaded one to be y, right? Or y is here. I'll just call it z, right? That is the expectation of z, right? Isn't it? So I can write this entropy to be E of log p x and y, right? Okay. So I put this one as a capital letters. Designating this as a random variable, okay? But you can shorten this to be some other name, right? Z, right? But it's the same thing, okay? So it's like taking the expectation of Z, okay? But in this particular textbook, he chose to use this notation, so I'll keep it with his notation, okay? So log P capital X, Y here means Carver and Thomas means this is a random variable. Okay? Small x and y, it is an outcome. Okay? X, capital Y is an expectation. Okay? So I have taken the expectation of this random variable, right? That's this part. Okay? Minus stays outside. So that's the entropy of x and y jointly is defined, can be defined this way as well. Okay? So it's an expectation of a joint distribution and minus in front of it. Okay? Okay, this one is okay, right? Now let's move on with the conditional entropy. So we define this to be defined from the left to right. Okay, so it is expectation part, and now the function part is this one. Okay, so log of p y given x. So this one is also two tuple, right? X and y we have to define in order to figure out what is the conditional probability y given x, right? So this one should be given to you in terms of a table, right? Conditional probability table, okay? And then once you have that, you need to be given one more thing, right? Because in order to calculate this, you need to know the joint distribution, okay? So the one thing that you need to be careful here is that here is a conditional, this one is joint, okay? So that's the distinction that we have to make, okay? So this part here is a function part, so this is a random variable, so log of p y given x, and then you are taking expectation of this, okay, with respect to x and y jointly, okay. So that's the notation that you need to be a little more careful. And then if you use this one and the expectation, you can use this one, and then you can write this way as well, right? Because joint distribution can be written as px times py given x, right? So since x is given, so you can bring this summation side inside like this. So you define this way, and then you come to this way, and then after you have obtained this, then I can write this as h of y x given small x, okay? So that's this part. So we can just say that, this is defined to be this one, okay? Okay. X is taking a particular value x, then that is this, okay? So, and then these two are the same, okay? And then in terms of notation, we are using this. So these are the some definitions that we have to remember, okay? Definition, okay? All right, so I will move on with this one. All right, and we will learn the chain rule part. Let's say joint entropy, h, x, and y can be written this way: hx plus hy given x. Okay, so we want to show that h, x and y jointly, by definition, can be written this way, right? And since this is the joint distribution, I can write as px times py given x. Right? That's the only change from here to here. And since this is log of a product of two terms, I can separate the two as a log px plus log py given x. Okay, it's just a log identity. Okay, and then I take the expectation basically, or the average. Okay, so bring this one to here, I obtain that. Bring this one to here, I obtain this. Okay. All right, so what happens to the summation of y part here for the first term? You may wonder, right? What happened to that term? Yeah, okay. So sum of all with respect to y is equal to 1, right? So that's what it is, okay? So whenever you have this inequality, you have to check by yourself, okay? Don't just assume. Remember, I have typos, right? So you just You shouldn't just assume that what I have here is right, okay? You have to reason through it, make sure it is right, okay? So it is right, okay? And I can define this as what? No, not define. Well, I can name this as what? By the definition of entropy of x, that is equal to h of x, right? How about this one? Oh, that's the conditional entropy, right? hy given x, because y is given and x is conditioned, okay? So py given x. So h of x plus h of y given x. There is no typo here, okay? I can believe this one is right, okay? And then I can do the this one all start with this part decomposed into x conditioned first, right? This is conditioned, x is conditioned. But I can also write this as y to be the variable that is conditioned, right? So p of y times p of x given y, I can decompose that way as well. And what would you see as the end result? Basically, if you condition on y, then this part becomes h of y, x given y, and the other part becomes h of y. Okay? The only difference from this line to that line is how you decompose this joint distribution into marginal and conditional. Okay? Okay? So far so good? So far so good. Okay. So after we have derivation, we can write h of x and y is equal to entropy of x and then plus entropy of y given x. Or we can write entropy of y plus entropy of x given y. Equivalently. They are equivalent. Okay. All right. Okay. So far, so good? All right. By the way, in this class, chapter 2 is the most difficult part. Chapter 2 and 3, because these are the parts that talks about the basics. After that, it becomes easier because we are applying this knowledge here and there, but same song and dance. So I am deliberately going slow for chapter 2 and 3. Okay, most of the people get lost in chapter 2 and 3. So after they have mastered this, rest of them, you can be on your own. Okay. All right. So I would like to read that textbook, because the textbook is given to you free. You have to utilize it, right? There are other more complex, more rigorous information theory textbook, but I don't like to recommend. This one is more insightful, less rigorous, but it's okay. We can understand. We are electrical engineers. We are not mathematicians. Okay. And we have done we can do the example, right? In this example, basically, you are given a table like this. So this table is a joint distribution, okay? So joint distribution of joint distribution p, x, and y. Once you have a joint distribution, then you can have the marginal distribution px, py, right? And then you can also obtain the conditional distribution, right? We have done this already, right? So I wouldn't want to repeat it, right? But I would like you to do it by yourself, so to get familiar with the notation, okay? So h of x, in order to find out h of x, what do you need? Let me ask you, okay? What do you need to calculate h of x? You just need to know the p of x. how do you get the P of x? So x is right here. It's a binary distribution. So you just need to know one parameter. Okay, you add these two. That is 3 over 8. 3 over 8. So I can just write this as h of 3 over 8. Then you are doing this calculation, I assume. Then if you use calculator, you will obtain 0.9544. So the answer that I expect is h of x is equal to h of 3 over 8. Then done. Right? Then we are moving to the next line. How about h of y? Can you give me the answer? h of y? Anyone? 정민석? 네? Yep. h 6 over 8. Okay, that's it, right? How about h y given x? And can you tell me what I'm doing right here? I'm doing, actually the answer is right here, right? So you can go either way, right? But I have chosen to do this way, right? If you have utilized the definition of h of y given x, you would have expectation of log py given x and minus sign in front of it. But you can use this equivalent statement as well. So in this particular case, you need to do this for x is equal to 0, which is 3 over 8. And entropy of y given x is equal to 0. And then plus the 1 minus 3 over 8, which is this part. And when x is equal to 1. Okay? And then rest of them. Now, what is this one? When x is equal to 0, right? When x is equal to 0, right? I need to know the conditional probability, right? Then it becomes 2/3. So I just need to know one of them, right? Okay, so because of here is a 2, divide the whole thing by 3 over 8, right? This 2 over 3 by 3 over 8, it becomes 2/3, okay? Okay, then I have an extra thing, the whole distribution, but you could just have given me h of 2/3. Close the parentheses. And same thing here, and then you get this number. Now I can ask you what is the joint entropy? Since I have calculated hx, hy given x, I can add the two, then I can obtain it. Or I can just use the full, the definition of joint entropy. I can go a long way and then arrive to the same answer. Okay. Okay. So all these things, the unit is bit. Okay, because I have taken log 2, not the natural log, right? Most of the part in this class we will use bit, okay, rather than nuts. But when we get to the Gaussian channel, we will use nuts as well. Okay. And here maximum entropy when uniform distribution. So h of x is less than or equal to log of the size of the alphabet. Okay. With the equality obtained if and only if x is uniform over x. Okay. So what is the difficult part to prove in this statement? The equality part, right? What is the difficult part? If x is uniform, is it difficult to show that equality is met? No, right? If x is uniform, you will immediately say that that is a log of size of the alphabet. So the difficult part is only if part. Only if part when you ask to prove, oh, that's the tricky part, huh? All right? Okay, so that only if part is one I owe you, right? We will talk about this after we talk about Jensen's inequality. Okay. Right. The next one is Jensen's inequality. So Jensen's inequality, I use this one to remember, right? Some textbook use this as a concave function, but most of the textbook, when the function goes this way, that is concave functions. This Carver and Thomas is the same thing. This one is convex. This one is concave, right? If you go this way, concave. And inequality, which way it should go, if you remember this picture, then you don't have to remember, right? Basically, you draw a code like this, right? And then you can figure out which way the inequality goes, okay? Right side or left side it should go, right? That's something that you have to remember, but when you don't have the lecture note right next to you, it's not easy to remember, right? It is always not easy to remember which way I have to go if there are only two choices, left or right, up or down, right? So this one is good at figuring out which way the inequality goes, if you remember this, okay? So here for random variable x, this is what we want to get, right? This is our objective, okay, in this chart, okay? So for random variable x and a function f, which is convex, so convex u, so when you say convex u, u is this way, so the curve should go this way, right? Okay, not this way, okay? Right? So in this case, average of function is greater than the function of average. That's what it is. Average of function is greater than function of average, okay? That's what we need to remember, okay? So in this particular function, f of x, which is convex u, where is the average of function? Average of function. So function is, so here is x, here is f of x, right? Y-axis is f of x, right? X-axis is the input, y-axis is the output, right? So this one says expectation of output, okay? Function of expectation of input, okay? So if we consider 2 points, x1 and x2, average is somewhere between the two, right? So for example, this one, okay? And then we can talk about f of x1, f of x2, and then average of that. So f of x1 is right here, f of x2 is right here, right? And then average of that. So it is somewhere between the two. Let's say this point, okay? So that is the average of function, the black point is, right? And this pink point is function of average. Average of function. So average of function is greater than function of average, right? So when you are, when you are confused which way the inequality goes, you remember this picture, okay? That's that. And if you apply the definition of a convex function, this part can be followed through, okay? So apply the definition of a convex function, okay? Then you will obtain this. And this is a theorem that Carbo and Thomas proves in his textbook, right? But if you apply the definition of a convex function, it comes through right away. Okay, so this theorem has two parts. Let's say you have a random variable x and convex function u, convex function f. Then expectation of function is greater than function of expectation. Okay. So average of function greater than or equal to function of average. Okay. This is for convex u function f. If the function fx is strictly convex function, right? Strictly convex function, then this equality is obtained if and only if x is a constant. Okay, so those are the two statements. One for the convex function, the other one for the strictly convex function. Okay, so those are the two statements, and you know the definition of definition of convex. You know the definition of convex function? Anyone? How do you define a function is convex? So I said that if you apply the definition of convex function, then this is obvious, right? That's what I said. So now I need to ask you, what is the definition of convex function? These days you can look it up for Wikipedia and then it will tell you, right? But can anyone make a statement about that definition of a convex function? In terms of shape, it looks like this, right? Can you define it mathematically? That's what I'm saying.
You have to, second derivative of the function should be over 0 or equal.
Yeah. So, for example of, let's say, high school example, let's say, high school example, like y is equal to x squared, right? X is a real number, right? Right? In such case, what is this one? Convex or concave? Convex. So how do you do that? Something like that, right? Do it twice, right? So always second derivative is greater than or equal to 0. It's a convex function. If it is greater than 0, not including the equality, what do you say? Strictly convex. So this is a high school version of definition of a convex function. How do you do this in graduate school? Anyone? 어디에? 요거? 그렇죠. 근데 조금 더 리거러스하게. 왜냐면 저것도 내가 생략한 게 많잖아요. 엑기스만 말하느라고.
컴백스 셋 정의를.
아, 너무 어려운데. 거기까지 갈 필요는 없을 것 같고. 두 점을 이었을 때. 오케이. So 우리가 이런 거 말하는 거죠, 지금? 이런 거. So this is the objective that we want. And then like the one that I said that y equal x squared, I define the space, right? So we need some interval, right? Let's say from A to B, right? We are talking about this function only over this interval, right? Outside this interval, some other things can happen, but we don't care, right? Because we don't know. What we want to know about it is only over this interval. Only over this interval, then we want to talk about convexity or concavity, right? And then we define some x1 and x2, 2 points, right, within the interval. And then we can talk about that line over there, okay? So let's say, suppose that lambda is a number between 0 and 1, x1 and x2, each one belongs to this interval, right? So for all such kind, right, any lambda and any x1 and x2, then what can we say? Say lambda f x1, right, plus 1 minus lambda f x2, right? So what I'm doing here, looks like I am doing the averaging, right? Averaging of function, right? And then I can also talk about function of average, which is lambda x1 plus 1 minus lambda x2, right? Which way is right? Always confusing, right? So remember that picture, right? If f is convex U, right? F is convex U, then that picture is right. Then that one says average is bigger, right? Okay, then this one is bigger, right? This one is no good, right? Erase that. Okay? So that's the definition of a convex U function. Definition. Okay? And then as you can see, this is the expectation of a function, right? This is a function of expectation, right? For the binary case. Can we extend this to the ternary case, quaternary, and so on and so on? Use the induction, right? Add one more point, do it, add another point, and do it again. And so that is given, that type of proof is given in Carver and Thomas, okay? So when you have a question, read it, but at least you need to remember the definition of the convex function. So that is the graduate school's version of a convex function definition.